Okay, so last time I gave an introduction to DMRG, and then today is focused on trying to use DMRG for electronic structure. So I want to sort of introduce the nature of the problem, and then talk about the QC DMRG approach, which has been used for a decade and a half now. Then talk about some newer work that involves thinking about sort of grids in some way. There we have show some 1D grid calculations for sort of toy models, show how we can take that in a partial way to 3D, and then the latest results where we're really trying to sort of do things more in a 3D fashion and really pave the way for real electronic structure. Okay. A lot of this work has been done with Miles Studenmeyer and a number of others along the way, including our Simons collaboration. Okay, so let's talk about the motivation and the key statement of the problem. So if you look at how we attack, as condensed matter physicists, how we attack a new strongly correlated material, the traditional way has been sort of to split it in two. So we have one group of people who do DFT sorts of things, and they may get input from experiments, and the output of that is a simple model, like here's a Hubbard model or here's a Heisenberg model with these couple of parameters. Not too many parameters, usually sometimes a half a dozen, sometimes one or two. Then the separate group of people analyze or simulate this model theoretically or numerically, and give some answers for that. And maybe they'll use DMRG for this. Okay, so before I talk about why we want to merge these together, let me ask a deeper question, which is, why are these super simple models like the Hubbard model at all useful? If you think of, it's like, how can I reduce this complicated material down to a Hubbard model with a couple of parameters? Okay, and so the answers are that all this is sometimes very useful. So sometimes we have very simple low energy degrees of freedom. So you may have a very complicated organic molecule that just has a spin 1/2 that's all we care about on each molecule. And it may be constrained by symmetry so that there's not many interactions that are likely to be reasonable, and things are local, and so you just have some sort of Heisenberg model with a few parameters. So that can happen. It's particularly true if you're talking about magnetic systems, that the Hamiltonians are sort of more constrained. The other thing is that we may be interested in universal questions. So when we look at the Hubbard model, we're trying to answer basic questions like, can we have repulsive interactions that give rise to superconductivity without any phonons? That sort of basic question. And universality says that if we're looking in the vicinity, if we're looking in a region of critical behavior, that a lot of different models may flow to the same critical point, and you get the same critical properties. And so if you're just interested in that, that's all you need. Of course, they'll all have different TCs and different other sorts of parameters. And if you're away from the critical point, they're all different. But it's sort of a question of what you're interested in. Okay? But so often this separation between these two parts of the work doesn't work. DFT may fail too badly. And you may have, another thing is that when you look at our results, as we've improved our simulations of things like the Hubbard model, we find that tiny parameters in the model, which we're not able to determine very well, can change which phase you're in. So, okay, you can try to map them all out over all possible parameters. That's boring, in some sense. But you'd really like to say, oh, I know this is the material, and I'd like to predict what its phase is, rather than just sort of mapping by, this is the answer that this model gives, so it must be the right model for this material. Another sort of attitude is that you may be, this is particularly true in quantum chemistry, but also just in sort of trying to understand real materials. You may want very specific accurate properties of the molecule or a material, and you're not so interested in universality. Okay, so there's lots of reasons to do this, and people realize this, and Christian has gave a couple of talks where we learned about another completely different sort of approach to try to go beyond DFT and build in a lot more where you're doing the correlation and the electronic structure together. Okay, so I want to try to do this from the point of view of being able to do DMRG and tensor networks, where I'm including the electronic structure at the same time. Now, if you do that, you introduce a whole set of complications, and you know the DMRG is already hard, and you're introducing all these complications. You got to consider basis sets, choices of basis sets. You have long-range Coulomb that you left out in the Hubbard model, you put it back in. You have a wide range of energy scales, including like core electrons or high energy virtuals. You have the full form of the two-particle interaction, which I'll talk a lot about. And you may even generate, because you've done this, you may even generate much more entanglement than you had before. So why should we make life so much harder and work on this? And well, the answer is that there's a big potential payoff. You know, there's potentially very broad usefulness if you sort of improve these things. You know, that it's a big field out there, and if you make progress in one, even in a narrow part, you still may have a high impact. You know, just as an example of how big this field is, my colleague Kieran Burke is the B of the PBE functional, density functional, very popular functional. I looked it up this morning. It has 92,000 citations for, you know, making a nice functional. So it's a big impact area, and so if we make some progress, even though it's hard, it can be very useful. So that's sort of a motivation. Okay. So let's start going through these things and see what the issues are. The starting point is to say, well, what about a basis set? Or more generally, you think of, I have a continuum problem where things are in real space, three-dimensional space, you know, microscopic points, and then somehow we have to put it on the computer, so we have to discretize it in some way. So almost all electronic structure methods use a basis. Popular ones are plane waves, which have, you know, some very nice properties, but as we'll see a little bit, they're almost useless for DMRG because they're completely delocalized. Okay, so we're not. I'll mention why they don't work, but we'll have to look elsewhere. Okay, and then in quantum chemistry, it's much more popular to use atom-centered Gaussian functions. So on each atom, you put a set of Gaussian functions. These functions are highly adapted. They're adapted differently for each atom to get that atom treated very well, and also the atom in its usual chemical environment. They're highly adapted so that it ends up with a very small basis, much smaller than your usual plane wave basis. There's different levels of completeness that you can dial in. There's a wide variety of choices, and it's tricky to know what is a good enough basis for your problem. In fact, if you're new in the sort of doing something, dabbling in quantum chemistry, and you show what you've done to a quantum chemist, my experience is that he's almost certain to tell you, oh, why did you use that basis? That's a bad basis for your problem. So it's an art, and that's a problem rather than converging in plane waves with some sort of energy cutoff. Okay, so after we for any of these basis sets, then we need to transform the Hamiltonian to the basis set. So we have this finite set of functions phi sub I, and the generic form of the Hamiltonian that you get, you can lump all of the single particle terms, the kinetic energy and the nuclear electron potential, into one matrix. I'll call it H1. Okay? And then you get the two-electron Coulomb interaction. And this goes into a much more complicated interaction that is sort of a general way of two particles scattering into two other states. And of course, you're used to this sort of expanded form in K-space. Even though the Coulomb interaction is actually a sort of point-wise thing. It's the density here times the density there. It's sort of like, why doesn't it depend on two variables? But this is more writing in sort of scattering language. Okay, and it immediately gives you this thing that depends on the number of basis functions to the fourth power. So that's not a trivial amount of computational work. Okay. The degrees of freedom in this problem are just those of a Hubbard model, empty, up or down, or doubly occupied. So if I'm doing DMRG and I have software like iTensor which can handle very general problems, you tell me, oh, I have a Hamiltonian that looks like this. Oh, iTensor can do it. A lot of software can do it. Okay, but then you look at actually how long it'll take to do it. And it's got bad computational scaling because of this n to the fourth terms in this piece. So what it looks like if you do it completely naively is that you have your calculation time for, say, the Hubbard model, which is the number of sites times this matrix dimension cubed. And then you multiply it because you have to keep track of all of these n to the fourth terms, and all of a sudden you have n to the fifth. And this is kind of a disaster because the m cubed is a big thing, and it's, you know, you're not going to be able to do very much. Okay. Nevertheless, we have quantum chemistry DMRG. So I sort of got this started back in 98 or 99, and then it's you know, gained some steam. But the first key thing is a trick, which actually Tao Zhang first used for trying to do the Hubbard model in momentum space. But it's a trick for sort of just combining operators within the framework of the DMRG algorithm so that it just cuts down on the complexity. So what the basic trick is, you have some sort of term like this, but let's imagine that we sort of separate it depending on, as you sweep, which of these indices are on the left block and which are on the right block. And let's suppose I is only on the left block. You sum up all the other terms into one term that are all in the right block. So you do this sort of summation, and then you end up working with a much smaller number of terms. And the work of sort of keeping track of these things is a lot less, and it gives you a big reduction. So it gives you a reduction in the effort from n to the fifth down to n cubed for the dominant term. Of course, there's still n to the fourth pieces. That comes in as sort of a term that's not quite as important, and n to the fourth m squared. And so that's your new scaling. So this is a big enough improvement that we could finally do at least, you know, tackle a very simple quantum chemistry problem. So with Richard Martin from Los Alamos, we used a basis with about 25 Gaussian functions. We transformed the basis to the Hartree-Fock molecular orbitals, and then just wrote down this generalized sort of Hubbard model with these sorts of tricks. And then we could treat this stretched water molecule and compare with some sort of nearly exact diagonalization and show that this was a feasible procedure. Okay, so this is you know, eventually sort of caught on to a certain extent. It's now one of the techniques in quantum chemistry. The leader in making that transition has been Garnet Chan, who's now at Caltech. And what can they do now? Well, you can do you know, 100 active orbitals, or maybe at the extreme push it up to the upper 100s. You can, you know, typically this is done where these active orbitals are selected from a bigger basis, and so you've got some sort of truncation of unimportant things. So in the most ambitious part, you only treat valence levels. So you keep, say, up to 100 active levels, and you use some sort of truncation, or you can try to integrate out the orbitals that you're getting rid of are like the core orbitals, which are almost fully occupied, or the very high-lying orbitals. And you can either try to integrate them out in sort of an RG sense, or you can do a simple truncation for rough calculations. And with this, you can do some impressive calculations. So this is a calculation that Chan's group did on the oxygen evolving complex. It's responsible for photosynthesis. I'm certainly not an expert in it, but it's an impressive thing. These you know, fancy molecules that are used in things like photosynthesis tend to have some transition metals in them, and it looks like a little correlated system in a solid state sense. And it has very complicated stuff that happens, and so that's a reason for using DMRG. There's part of doing this sort of thing that I'll get into later is that you want to try to keep the orbitals as localized as possible. There are localizing procedures that are part of quantum chemistry, and that's an essential part of doing any sort of big system like this.
Is there anything particular about it that is 1D-like, or is it essentially very 3D?
No, it's not particularly 1D-like. So DMRG gets its power, you know, if you have a 1D system, it's really in its, you know, its ideal area. But DMRG is also just a very efficient algorithm for truncating things, even if you don't really have a 1D system. And that's the sort of thing for something like this, where it's still useful. But this is still a long way from what we can simulate with local models like a Hubbard model. So if I have a Hubbard chain, I can do thousands of sites, and it's not so much trouble. And here we're much smaller than that. And so we'd like to move from this region here to what we can do with models. And the reason for this big discrepancy is we still have this n cubed, essentially. And there's also some issues about entanglement that come in. Okay, so let me talk about the entanglement issues that come in. Now, if you do the localization I sort of mentioned in this, they try to take care of it, but it's still an issue you have to think about. Okay, and so let's go back to yesterday's lecture talking about the area law and low entanglement and how that works. So the area law is a real space thing where we have a system divided into two parts, and the area law says that the entanglement entropy is proportional to the area of the cut between these. And that translates to a DMRG calculation where the matrix size has to be exponential in that area. Okay, so what about a system in a basis? Well, suppose we think about going all the way to K-space. What this means is that if you think about, well, what's an area between the two systems? Well, it depends on what the Hamiltonian does. If two K points can scatter and go to two far distant K points, there's actually no locality at all. Everything talks to everything in K-space to first approximation. And what you get is a volume law. So the whole basis for DMRG falls apart. There's no locality. Now there is an exception, which is if you go to K-space and you're talking about a non-interacting problem, you've already solved the problem. Well, DMRG won't make it any worse. You know, if you have a non-interacting set of electrons and you go to K-space, you've already solved the problem. You can go to those K-space orbitals and they'll just be, you know, you sort them and they're all fully occupied until you get to the Fermi surface and then they're unoccupied. And so you only need one state with DMRG for that case. But this turns out to be a very sort of localized region. If you do this in the Hubbard model and you start turning on a U, you'll find that you very quickly see this volume law and it becomes a bad way to do the calculation. Okay, but we do need to keep in mind that this, so I think of this more generally, instead of K-space localization, you can think of energy localization. If you think about a single atom, you still want to think about energy localizing it. In other words, you want one of the orbitals that goes into your DMRG, if you've got a 1s state that's buried down there, you should make that 1s state one of your orbitals. It'll be almost doubly occupied, and you'll make use of that. And that doesn't conflict so much with keeping it local, because these core orbitals are also very local. Okay, so now let's think about a basis which is has some sort of width to the functions. Well, there's been essentially no theory on this that I know of, but we can just sort of try to guess. Suppose that the size of the basis functions was lambda. You might expect that you should actually multiply the area by this lambda and say, well, within this region, they're all talking to each other. So we'd have some area law with an extra lambda in it. And so obviously you want to keep this lambda to be very small. Okay. So again, this is it for K-space, lambda would be the size of the system. It's going to be a disaster. Okay, so what would be the, yeah.
In the Hubbard model, if U is 0, then you just have product state in second quantization.
Right.
And then if you turn on some U, you can think of it perturbatively. So does the volume law kick on or turn on immediately, or is there some critical U where you go from?
Yeah, so Reinhard Nowak and his student Ehlers studied this in the Hubbard model, and they were trying to see if there's some useful region of small u where you could have it quantized in K-space and the volume law doesn't kill you too fast. But they found that it was, you know, if you're at u equals 1, you're in a bad region. So that means you've got a very small u region where there's lots of alternative techniques that you could be using. You know, you're not going to have a sign problem. You can do all sorts of things. So it's not a useful sort of approach. Okay, so what does this tell us about what might be the best basis for doing DMRG in quantum chemistry? Well, you can have some different choices that you can try to explore. You could try to make it just completely as localized as possible. You could sort of localize it atom by atom, and then within an atom try to localize it by energy. And then there's another version which is actually what's used in the state-of-the-art quantum chemistry, which is called split localization, which is you try to localize as much as possible separately the things below the Fermi level and above the Fermi level. Now, a problem with all of these methods, this sort of trying to localize, is it just doesn't work very well in the standard basis sets. So suppose let's just say, suppose I try to localize a plane wave basis set. That's easy to localize. So you say, oh, I have a plane wave basis set, and I try to represent a delta function at some point in space. Well, what you find is that, do it in 1D. What you find is that your localized function is a sinc function, a sine x over x, okay? Because it's just like that's the integral up to a cutoff of plane waves. And so it's like, well, how fast does sine x over x decay? It decays as 1 over x. This is a very delocalized function. So if you just take a sort of arbitrary kind of basis and you just try to localize it as best as you can within that basis, that's the sort of thing you get. These things have these tails that can stick out a ways. Okay. So that's a key problem that we want to try to address. Okay. Then this is sort of reiterating what I had before about the computational issues and where we want to be. Okay. So let's, this is the same slide as last. Go over to here. Suppose we had a grid representation instead of a usual basis. What would that do to the Hamiltonian? Well, in a grid, if you make the standard finite difference approximations, you would just say, oh, it's just Vij ni times Nj. That's an n squared instead of an n to the fourth for the 2 electron part. That's a big win. Why don't we do that? So if you look at, and you can still do the complementary operators tricks on this. So this would turn into an n squared times m cubed. It would give you 1 factor of n with the complementary operators trick. And so this is a very interesting thing to think about. Another thing is that there are some further reduction that's possible by tricks with matrix product operators. So I didn't really talk about matrix product operators, but it's like seeing how you write a matrix product state and doing the same thing for operators. And there's some tricks that you can do with that reduce the scaling. It's called matrix product operator compression. And you can get it all the way back down with the grid, potentially down to the scaling of the Hubbard model. Okay. So, and then, of course, the other thing which I'll get back to is that it depends a lot how this works on what sort of grid spacing you can do. Okay, but as a first stab at exploring this area, I had a project that's gone on for quite a while with Kieran Burke, and it's to look at toy 1D systems. So these are not at all real physical systems, but let's say you live in 1D, you live in the continuum, so you have potential functions, you have long-range interactions, and you want to make a little laboratory for exploring DFT and other approximations, like double counting, which we heard about in the last talk. You know, suppose you want to explore double counting where you have exact results for everything and you can really have a fine control of everything. This is what our little laboratory was designed to do. So we set up a 1D problem. We choose some 1D potentials that are, you know, we have a couple of choices, but they're designed to mimic particular aspects of the 3D world. Okay? And then we represent it with just a finite difference grid. Okay? And we use all of our DMRG tricks. Okay? So we could also solve the electron gas with DMRG. You can do it with quantum Monte Carlo too. But you can use this to get a correlation energy, and so you can implement your LDA. Okay, so you can really set up your lab. And then we've done various experiments. And so here's an example where we treated 100 hydrogen-like pseudo-atoms in a line. And you know, this was used 4,000 grid points, and the DMRG was not a super hard DMRG. And then we could do DFT on it and compare the results. And this was an example where our hydrogens were sort of stretched beyond equilibrium, so it turned into a strongly correlated problem. Okay, and so if we look here, this is just sort of showing how the middle of the chain differs from the edge of the chain. But if we look down at the bottom, we see a comparison between the essentially exact DMRG results, an unrestricted local spin density approximation and restricted LDA. And you see these different curves, and you see how, you know, LDA is having a bit of a hard time with this problem because it's strongly correlated. And you know, there's the green one is sort of in between the red and the blue. It might be able to, not be able to see it. Okay, so that's something that we've made some use out of. Okay, but I want to go on beyond that and try to do real 3D problems. Okay, so let's think again about that was a grid that had a grid spacing of 0.05. Suppose we just said let's do a grid for DMRG, and for a 3D problem, let's start small with H2. Okay, so if I put this in a box, 10 AU by 10 AU by 20 AU for H2, and I use this grid spacing of 0.05, it gives me 10 to the 7 sites that I would have to feed into my DMRG black box. That's way too many. Okay, so that's the problem of a direct. It's just, you know, it may scale well, but if you have, you know, you make it a little bit bigger, you could be in the 10 to the 9 range. You can't do DMRG with, you know, 10 to the 8 sites. Okay, so we need to do something better than that. Okay, so next step is suppose we think about a grid in only one direction to partly take care of some of the problems, but we use a Gaussian basis set for the transverse directions. So that's slice basis DMRG that I did with Miles Studenmeyer. Okay, so we're thinking of a chain molecule, which will be good for doing DMRG. The application that I'll be showing are on a sort of fake 1D molecule, just hydrogen atoms equally spaced along a line. We'd like to take the limit that the line goes to infinity, so it's like a 1D solid, but it's built out of 3D hydrogen atoms. Okay? So we put a grid in the long direction, and what that grid does is if you now look at chopping the system in two to calculate the entanglement area, you have a sharp grid distinction, so it's like a sharp wall. And so you don't get any extra entanglement from some sort of lambda. So you've taken the direction that you're going and you made the lambda go to 0 for this you know, width. Okay, and then we try to use standard Gaussian basis sets, but just use 2D projections of them. Okay, and so this sort of thing sort of shows this, like, you know, these are sort of symbolic things for a 2D function living on a grid. Okay, so you can think when you do the kinetic energy, you use finite differences. When you do the integrals, you can think of these as like having a delta function representation in the z direction, and you have integrals to do to set this up. Okay. What do these transverse functions look like? Well, you might start with a set of Gaussians. I'm just showing the S functions, you know, that get P functions have an extra node in them. We don't keep too many of these, but so here's 3 S functions. We have to orthogonalize them to make them feed into the DMRG. So here's an orthogonalized set. But we take particular linear combinations that if we look along, say, the hydrogen chain, we have a different functions if we're lined up with the nucleus. You need some sharp functions there. We have different functions if we're right in the middle of a bond. So the top two are through the bond. So these would be the functions that we would use in this case. And then if we have a slice through the nucleus, we have, it's just a little bit sharper there. And this is all comes out of, sort of naturally out of projecting some of these Gaussian basis sets down to a slice. Okay? And a slice is just one particular z direction grid point. We think of it as a plane. Of course, this is not variational. But it becomes exact in a nice controlled way as the grid spacing goes to 0. But then it becomes variational. But then you have a further, to try to get to the full exact result, you'd have to make the number of these transverse functions also get large. Okay. So constructing the Hamiltonian, so if we look at the integrals that come in to define the VIJKL, we have this delta function that reduces the number of non-zero pieces to the number of slices squared. And then it still has sort of the 4th power of the number of orbitals per slice. So if we look now at, how long do these calculations take? Well, just this locality here reduces the scaling by a factor of n. Okay, but then there's this other thing which I briefly mentioned, this MPO compression. And let me say a little bit about this sort of compression. It's sort of derived by thinking about compressing a matrix. So the standard way, if you look in numerical recipes about compressing a matrix, they'll tell you how SVD is great for compressing a matrix. But if you think about how that really works, if you made a 2D plot of the matrix elements of your matrix, if it was really smooth as a surface plot, that would be an example where you would know it would compress nicely. You can do this sort of, summation of a few row vectors and column vectors, multiply them together in a small number, and you can represent them that way. And that's related to the DMRG compression for low entanglement. Now, if we look at the interaction in this case, it doesn't look smooth. So we're thinking about some sort of Coulomb interaction where the diagonal here is where the particles are on top of each other. So it's really like a ridge. It's like a sort of ridge going along the diagonal. If you do an SVD on this whole matrix, it doesn't compress really much at all. The limit where you might think it'd work best, which is a totally local interaction, would be just you're trying to compress the unit matrix. And the unit matrix has every singular value is the same. So you can't do a full compression, but you can do a compression based on considering these sorts of off-diagonal blocks. So if it has a ridge-like structure with a peak along the diagonal, then this part will be smooth. Okay, so that you can compress. And so you can translate this sort of funny way of compressing a matrix directly into the tensor network language and make an MPO with a small bond dimension. Okay, so this general sort of approach, which can be generalized to the sort of quantum chemistry DMRG, is shown here. And then we also talk about this in our slice basis paper. So this actually gets you another factor of n. And in fact, for the slice basis and for the hydrogen chains, it takes you all the way down to the scaling of the Hubbard model, all the way down to where we want to be.
Is it a single MPO or is it a sum of MPOs that you need to represent to describe the?
We have just a couple of MPOs. We do the ups and the downs separately, but mostly it's just one that this sort of compresses it into. Yeah.
The bond dimension of that?
It might be on the order. Well, okay. So we did a similar trick in the 1D toy systems, and there we could get away with a bond dimension of on the order of say 30 for the MPO. And when we do the slice basis, then it starts creeping up to on the order of 100. And it depends on how ambitious you are. Okay, so in the end, once you've done this setup, you've transformed your hydrogen chain system in 3D to something that looks sort of like a Hubbard ladder. And we do the DMRG pretending sort of it's a Hubbard ladder. A Hubbard ladder, you sort of have a path through the system that goes in this snake sort of thing, or the snake is usually when you draw it the other way. That doesn't matter, but you sort of go through it on each slice orbital by orbital, and it makes a fine DMRG. So this surface plot of the electron density through a plane containing the nuclei is from one of these slice basis calculations. This plot is a key plot. This is actually the time for one DMRG sweep for this system, and it's versus the number of atoms going up to 1,000 atoms. So this is 10 atoms, but we could actually go all the way to 1,000 atoms. If we want to do 1,000 atoms, we were only doing one slice function, one orbital per slice. But calculation time is strictly linear from way down. And so the total calculation time on a machine in my office was on the order of a little over an hour for one DMRG sweep, even for 1,000 atoms. Okay, so this scaling has really had a drastic payoff. If you look at the accuracy, well, it's just sort of what you might expect for this sort of slightly different way of doing the basis. Your grid gives you really high accuracy in one direction, and then the limitation is how many transverse functions you have. And you can compare it if you had just used the Gaussians that fed you the transverse functions. And so this, like green one, you see sort of like, well, it's very similar. These two green curves are the Gaussian basis that something came from, and the sliced version of them for 10 hydrogen atoms, and they're very close. As you put in more functions, the sliced basis tends to do a little bit better because it has this infinite resolution in the z direction. And so you see they're very close, with the sliced basis results being a little bit better. Okay. But this is, and the limitation that I'll say a little bit more about is the scaling isn't so good when you try to pour a bunch of transverse functions. You know, up to about 10 is fine, 12 is fine, but if you tried to do 100 transverse functions, this end-of-the-Voigt scaling, it'd be hopeless. Okay. So we can actually do some physics with this, and it's sort of an interesting problem. It's not an experimental problem unless you can build a hydrogen chain. You know, maybe there'll be something that can build a hydrogen chain, but it's an interesting physics problem, which is, you know, when you've looked at this plot, you see this dimerization in the electron density, okay? And the question is, oh, what is the sort of physical properties of that? So in particular, so the densities here is lower than here, and it's associated with the finite boundaries, but it's possible that this could be a true broken symmetry, where if you did an infinitely long chain, it just is dimerized. And you know, when you look at the calculations, that's the way it looks. Or it could be that in the limit of an infinitely long chain, it gradually fluctuates away. Okay, so that's the question we want to address, and sort of what's the critical behavior of this. Okay. So we'll do it as a function of the separation. It's like, you know, a typical case will be 2 atomic units, and the sort of equilibrium is around 1.4 atomic units. Since this is a discrete symmetry, it's possible that it's broken. You know, continuous symmetry, it would have to be, at best, algebraic decay. This system is very similar to a half-filled Hubbard chain. You know, a hydrogen atom is sort of your ideal case for thinking about a Hubbard site. In the Hubbard model, there's no density in the middle. You know, we only have density on site. So how do we even define this? Well, this is sort of, in the Hubbard model, this would be more associated with the hopping on a bond. That's sort of tied to an extra density in the middle of that bond. So we could take a Hubbard model and think this system is very much like looking at dimerization in the local kinetic energy between two sites. Okay? And we know in the Hubbard model that this actually does not break symmetry, at least for nearest neighbor hopping. Okay? You can also tie this to the Heisenberg chain, and this extra bond density actually corresponds to S dot S. And you also see this sort of dimerization if you do a simulation with open edges of a Heisenberg chain. So this is actually something very familiar, but if you put in the Heisenberg chain, this is understood very well. If you add an extra J prime for next nearest neighbors, you can go to a regime where it goes from being algebraically decaying to a true broken symmetry at this particular point. Okay. So in this system, we can't. There's no way we can say that it doesn't have these extra couplings if you reduce it to a simple Hamiltonian. So we want to find out what this does. Okay, so only an accurate simulation, sort of putting in these details, is able to tell us what we've got here. Okay, so here's some data. Here's 20 hydrogens and 40 hydrogens plotting. So we get a nice, you know, we have this grid along the z direction, so we get a nice, connect all the points, and you get a nice continuous curve. And then we can look in the center of this system and look at the alternation between the even bonds and the odd bonds and make that as a measure of the dimerization. We want to look at that in the center of the system. Okay, and then over here we can do the same thing for a system twice as big and look at this dimerization. And we'd like to know how this depends on the total length of the system. Yeah?
What happens if you have like odd number of sites?
Oh, then you get, it's essentially like a spin-on in the system. If you have an odd number of sites, you'll have an extra up or down, and it will be distributed about the system, and it'll look like a sort of a spin-on. Well, it'll make a particular shape which we can look at, and we've looked at them many times in the simpler models. So that, I mean, that's an interesting thing. You can look at it, but the usual physics is like, oh, I've got a spin-on in my system, and it's doing it. Well, it's like the spin-on acts as a domain wall, and so it makes a superposition with the different positions of the spin-on moves the domain wall. So it smears it out in the center because the domain walls move back and forth. You get this sort of butterfly shape. Yeah. One of the very early things he saw in doing DMRG on spin 1/2 Heisenberg systems, like, what's this butterfly shape, you know? So very familiar from that. Okay, so we measured this. So with our experience with the spin chains, I'm focusing on this particular way to measure this property because that's what works for the spin chains. So here's the dimerization as a function of the number of atoms plotted versus 1 over the number of atoms. And you see that this dimerization is not going to a constant. It's falling, and it's not falling in a straight line. Okay, and if you look at how hard we had to work with the DMRG to get this to work, we had to work pretty hard to get this critical behavior. This is something that depends sensitively on doing the DMRG accurately. And so here are the energies that we needed to, we kept more and more states. The energy became extremely accurate. So this is varying in the 4th digit past the decimal of the total energy between these couple of points. So we're trying to get like 8 digits or so, and that's what's needed to make the dimerization, because it's got a lot of quantum fluctuations to make the dimerization come out very precisely so we can make a curve like this. This is, yeah. But not per, it's not per atom. It's, yeah, so, 100 atoms. So it's a very tiny, very tiny energy. And we don't need to get the basis set complete to that degree. There's a huge error in the lack of completeness in the basis set. So we're so you can say, well, if I have this huge energy, why would I ever pay attention to these tiny energy differences? But this is back to the idea of universality. If I have a system in a particular basis, I can think of that as like a fancy model, and I need to solve the model very accurately, and then it should be in the same universality class as the more accurate model. But that's a little bit of a subtle point. Okay, so if you plot this on a log-log scale, you see this nice scaling. If you did this on the Heisenberg model, you would see almost the same thing. So this is fairly convincing. Now, the actual slope that you get, we think it should be 1/2. But this is known to have significant log corrections. So the log corrections make it very hard to see the actual thing. So when we do this for the Heisenberg model, where we can really do big systems and nail it, we see the same sorts of deviations in the slope from this predicted 1/2 because of the log corrections. Okay, so this is sort of, I think, given how close this looks to what we see in the spin models, I think this is pretty conclusive. So the conclusion is that at moderate to large separation, the dimerization is not a broken symmetry. It has this power law decay away from the edges. Okay. Now let's go back to trying to improve our ability to go, say, beyond the hydrogen chain. Okay. So we want to go beyond slice basis sets. The key problem being that we can't increase the number of functions per slice very much, or it doesn't scale well. Okay, so let's start thinking about this grid again. So suppose we could make a very coarse grid. When I gave this estimate of the number of grid points, that was putting in this spacing of 1/20th that we used in the 1D calculations. If your grid spacing was only of order 1 atomic unit, you'd be back in the ballpark. You'd have like on the order of a few thousand functions, and you could do something. Okay, so is there some way we can think about doing a very coarse grid? Now, when you just do finite differences and you try to make a coarse grid, it just doesn't work very well. Maybe we just don't know how to do it very well, but basis functions tend to work just much better in electronic structure. So suppose you could do something that partway thought it was a grid and partway thought it was a set of basis functions. Okay, so what we want to think about is you have a grid, and then you put these localized functions on them on each site. Okay, and this is a particular sort of home-cooked version called a Gauss-let. Okay, and that the black is just showing one of them, and then the translations. This is sort of your 1D basis. Okay, so let's suppose that we could make some functions like this that had a set of really ideal properties. Okay, what would the properties be that we'd really like? So we'd like minimal width or uncertainty in x and not p, but p squared, because we want them to be real functions, not plane wave-like. Okay, so everybody knows what, if I just had this criteria, what would I have? What would be my function? Minimum x and p uncertainty. A Gaussian. That's what you learn in junior level quantum mechanics, right? Oh, let's just do Gaussians. That's our perfect basis function. Except when I throw in requirement number 2, orthonormality. Now, the proof that the Gaussian is the best thing without the orthonormality, that's easy enough to put in the junior level quantum mechanics books. Okay, but the orthonormality, this all of a sudden was an unsolved sort of problem up until a few decades ago. And it's still sort of only a partially solved problem. There's lots of answers, right? So the function to be orthonormal has to have these wiggles in them that when you integrate 2 of them that are not on the same one, it cancels out and you get them orthonormal. And that's all of a sudden tricky. Okay, so I'll talk about how you do that. But we also want these to be complete in some sense. So the standard way to think about that is it should exactly fit a polynomial up to a specific order, which should be as high as you like. And then the last criteria, which is sort of something you don't hear about very often, is it's very useful to make it integrate like a delta function for test functions that are polynomials. So we all know how to make a mock-up broad delta function. It's like, and then you take the limit that goes to 0, and it integrates exactly at that point. If you want to make it a little bit wider, you should make something with these oscillations, because if you start taking a function like this, you can make the oscillations cancel out the curvature, and you get a wider function that still integrates like a delta function. So we want that property up to some polynomial order. So it turns out that if you specify all of these properties, then it gives you a drastic reduction in the scaling of our 2-electron integral. It takes it from the form that looks like you're in a basis to where it looks like you're on a grid. And it's all tied to this delta function property. It's like, it's like a grid is like delta function points, and you get this Vij instead of Vijkl. Okay, so if you just have this function that looks like this with the delta function property for smooth functions, it acts that way. Okay, so diagonal approximations, we call these diagonal approximations with local functions. Okay, so it's the derivation is this is sort of the whole derivation. It's super simple and it's not very rigorous, but but we have lots of numerical tests that show that it worked very well. So let's say our function, our Gauss-let is g of x. It has this orthonormality. It has this delta function integration property. Let's just look first at the one particle potential, because that's a little bit easier. So we have a one particle potential u of x, and if we threw that into the Schrodinger equation, we might have a wave function times h. We'll have a part of it is the u times the wave function, gives another wave function. Okay? And we want to get this piece right, okay, for arbitrary smooth functions. So the standard derivation is to expand the left and right in the g functions. If they have the delta function property, the coefficient of each of these expansions is just the integral with the function times the wave function itself. Okay? And if you just plug this in the standard way, you'll get the standard formula that psi I is this matrix uij times phi j. So that's the standard single particle matrix for the potential. Okay, but we just think about this in a little different way. We say what we really want is to get psi of x is u of x times phi of x. So let's repeatedly use this formula and that formula and evaluate them at x equals I. So psi at x equals I by this formula is the coefficient. Okay, but evaluated at x equals I, you just plug in xi, or I in this case, and you get this, and then you use that formula on each of these, and you get this very simple formula that is not a matrix, it's just multiplying. Okay, so it's just from using these two things at once. Okay, so this is not exact. It's sort of based on the assumption that your basis set is complete and it fits with polynomials, but it converges very rapidly as you make the grid spacing smaller. Okay, so this diagonal approximation is a very useful thing. It's not so important for the single particle Hamiltonian, but for the two particle Hamiltonian, it works exactly the same way. It reduces your 4-index guy down to a 2-index guy. Okay, and so that's what you can use with these kinds of functions. And it makes it seem like you have a grid, but you have a function which sort of works better. Okay. Okay, so how could we get this sort of magical function? So it turns out that this is, the solution to this is sort of related to wavelets. There's lots of different types of wavelets. A lot of the wavelets that you see in the textbooks are not they don't look like this. They're sort of fractal looking. They're not as useful for our purposes. Okay, but there are some wavelets that look a lot like this. This Gauss-let is sort of a homegrown one, which came out from tensor networks, actually. So I mentioned last time that this Mira tensor network is actually related to wavelet theory. And Glenn Evenley and I did a number of explorations of that. One of the things that we could do with that was we could use wavelet theory to build an analytic Mira tensor network. That was the first analytic Mira that people wrote down. And then we also did the reverse, where we used ideas from tensor networks to design nicer wavelets. The main thing that we wanted here was it's nice to have a symmetric wavelet, and the standard theory sort of produces unsymmetric wavelets. So, okay, so we use these. So that's sort of the starting point for making these Gauss-let functions. Okay? And then we can write them in 3D just by multiplying them by x, y, and z. Okay, so those have better properties. The diagonal approximation we can test in a sort of approximate, sort of 1D potential world to see if these things work. Okay, and so this shows the convergence of a Gauss-let basis for some particular potentials, just for a single particle problem in 1D. Okay, and this is on a log scale versus the spacing A. So we really want to be able to use a bigger A than this sort of 0.05, and you're doing quite, you're getting a lot of the way there. Okay, then this is testing the solution by when we compare putting in the full Uij part of the Hamiltonian and this diagonal approximation. So some of these are diagonal. There's several versions of the diagonal approximation. But the key thing is that they all converge to the same thing. They all converge rapidly to the right answer. So the diagonal approximation, it's not exact for a fixed spacing, but it converges rapidly to your exact answer. Okay, and here's a couple of other tests. You can throw in extra functions with singularity properties into the Gauss-let basis. But move on. Okay, next step is it really makes more sense to have the spacing between your functions smaller near the nucleus than it is out in the tails of a wave function. Okay, so can we design this into this sort of Gauss-let basis? Okay, so the way you can do that is you can make a coordinate transformation, which is shown in this box. So what we're going to do is we're going to have a U coordinate where every Gauss-let is on an integer spacing. But then this coordinate transformation here maps us over to the x-axis, which automatically gives you compressed spacing right near our nucleus, which is assumed to be at 0. Okay, and so here's an ansatz for a transformation. This ansatz says, a reasonable justification, so we sort of took it as an ansatz. Now, when you do this transformation, you need to put in a Jacobian factor to keep the orthonormality. So you do a transformation of x to u of x, but you put in this square root of u prime, which is just a Jacobian factor. So when you check the orthonormality of your new functions, this Jacobian factor cancels, and you end up with orthonormality. Okay, so here are these transformed functions. You know, they get sharper when you squeeze them in, so the normalization is fixed. And you get these functions that really spread out in the tails with a very big spacing, but they go sharp at the nucleus to resolve them. Okay, so that's a way of sort of getting our variable grid spacing with this sort of funny thing in between a basis and a grid. Okay, so then how do we take this to 3D? Well, you could just take products of the three functions, but when you throw in this coordinate transformation, the coordinate transformations are pretty easy in 1D. You know, we just have this u of x, you put in this inch. But if you try to do it in 3D, they get complicated and hard to work with, and it's very difficult to do the integrals. So we chose to do a thing where we keep it in 1D, but do sort of particular slices. We sort of make it a product of 1D distortions. So there's a u of x for z, then y, then x. Okay, but we can adapt the coordinate transformations sort of depending on where we are. So we think of it as slicing. So here's this picture of slicing. This could be just the slice basis, and say there's some atoms here. We're going to do the coordinate transformation so that we bunch up the functions. You know, first we're just thinking of it as a 1D problem. We bunch up the functions near this atom and near this atom and spread them way out there. Then we sort of make a grid in the y direction. So we come up in this direction. And the thing is that when we're on this slice, we use a fine grid because we're still near the nucleus, but everything is coarse along this direction. Okay, so that's what we call multi-slicing. Here's sort of a picture of what it looks in 2D. And it's sort of a nice compromising of sort of bunching up the functions near the nucleus and spreading them out far away in a way that still leaves the numerical part of the problem easy because everything is a product of 1D functions. Okay. So we have results for this also. We've been using it on the hydrogen chain again. We're now not trying for 1,000 atoms, but we're trying to get the exact result on just H10. And by the exact result, the correlation, the DMRG is going to get that exact anyway. But we would like to go to the complete basis set limit, like you just did this purely numerically for H10, and we want to get the full answer with no basis set approximations. That's what we're trying for. Okay, so in our Simon's collaboration, we studied this, and we've looked at lots of different methods that come from quantum chemistry and from solid-state physics to see how well they do. Now, the left thing shows where we're not trying to go to the complete basis set limit, but we just stay at one basis set. So this is a pretty simple basis set. This is a double zeta basis set, and this is the exact result, which is taken to be the quantum chemistry DMRG value. So that's essentially exact. Okay, and then you look at what other methods do. Okay, so for instance, we have coupled cluster of a couple of types. And you know, they're doing reasonably well, but we can really try to resolve fine differences. Okay, now over here we try to, and so this is all from sort of this Hubbard benchmark, and it doesn't show any of these new results yet. Here I've gone to a more complete basis, a quadruple zeta basis. Okay, and the first thing you see is I make the plot of all of the results that we had in our database, is there's a lot fewer results. So if you make the basis set more complete, the methods that are more difficult to do drop out and you can't run them, right? So they just weren't run. So you have a smaller set, and some of them are very accurate. And then you're still sort of far from the complete basis set limit, which you try to estimate. Okay, and you go to 5 zeta, and there's only 2 of them left in the database. Okay, so that's what we're trying to do. We're trying to go to this limit of the complete basis set limit and nail this down. So here's sort of what we got for that. So we have this transformation that sort of governs the overall spacing, and this is the key parameter of that. And we look, and these lines are sort of the lines over here. So we have double zeta. The triple zeta is not shown over here, but this triple zeta, quadruple zeta, 5 zeta. And we just sort of systematic. It's not totally, smooth, but it's pretty systematic. We just converge right to where we think the extrapolation should be. Okay. A few more results. So during the course of this, you're doing a DMRG for each of these points. How hard is it to do that DMRG? We're sort of doing state-of-the-art electronic structure. How hard was the DMRG part? Well, we can judge that by the number of states we had to keep and how easily it converges. We didn't even have to keep that many states. So we go up to 280 states. You can do a nice extrapolation in the truncation error and get a very nice result. So this is a really nice DMRG. It's a lot of the quantum chemistry DMRG, because of the non-locality of the basis sets, it's more difficult to converge, and this was easy. Okay? A few more comparisons showing how accurate we are. The quintuple zeta and the Gauss-let DMRG are on top of each other in this curve versus the spacing. Okay, and let me switch to a more recent version of this last fig. Oops, no, that's it. That's the more recent version. Okay, so finally we have this comparison of the best results for H10 in this Simon's database. Okay, so we have an AFQMC, which has done really well. This MRCI plus Q quantum chemistry method has done very well. The unrestricted coupled cluster is not doing as well. Chemical accuracy is sort of setting the scale for this. Okay, and when we started these sets of calculations of sort of all of this set of things, we didn't know which of these curves in this bunch here were actually more accurate. So what the benchmark comparison was done against the AFQMC because we thought that was the most accurate. Okay, but when we did our Gauss-let method, what we found is that we were systematically converging to something that was not the AFQMC, it was another QMC. Okay, so this is the diffusion Monte Carlo done by Sandro Sorella. We found that we agreed extremely accurate to that, so that's now our reference, and we look at the deviations in the energy as a function of R, and we just converge to, very accurately agreeing with that. And now we can see the sort of errors in some of the other methods, which are, sort of at the sub-millihartree level, but, at this level of accuracy, we can see that. Okay. So that's it. So in summary, when you try to apply things like DMRG, and eventually when we go beyond 1D systems, we would like to think of fancier tensor network methods that are using these basis function tricks. You have to set up the problem, and a key lesson is that the performance of our methods depends very strongly on how you set up the problem before you feed it into your say, tensor network method. Okay, and in particular, the locality and the basis sets can have a huge benefit in doing the DMRG for electronic structure. I haven't shown you any fancy DMRG. The DMRG at the end of the calculation, after you set it up, was standard and pretty easy. Okay, well, there was the compression trick, but other than that. The setup makes a huge difference, okay? And so this new sort of way of doing it using wavelet technology and this diagonal approximation is sort of crucial. This drastically improves the scaling. So we get, for these chain systems, we get a computational scaling that's linear in the number of atoms with very high accuracy. And one thing I didn't mention is that along the way, we started talking to some people from Google interested in quantum computing. And they worry a lot about this computational. They would like to do quantum chemistry on their quantum computers, which are now at 72 qubits. Okay, and so a key factor is not necessarily how many qubits you have, but how many gates you have to apply. And the number of gates you have to apply depends on this n to the fourth versus n squared that I kept mentioning. Okay, so that struck them as very interesting, and so we've been trying to think about how this sort of technology can, the black box at the end of the calculation, it can be DMRG, it could be a tensor network method, or maybe sometime in the future it'll be a quantum computer. And so we're exploring that. Okay, thanks.